Hi everyone, my name is Andrei. I'm a PhD student at the Institute of Science and Technology Austria, where at the group of Professor Alistair, we work mostly on efficiency for machine learning and specifically on efficiency for large language models. And today I'm going to present our latest work that's called QuEST, Stable Training of LLMs with 1-bit weights and activations, where we targeted a very specific thing, that is LLM pre-training, where we actually want to obtain models that are efficient from the start and utilize efficient kernels when they're done training and are used during inference. We did this work together with Jali Chen, Sarush Tabish, Roberto Lopez Castro, Magdalena Dunn, and Professor Alistair himself. And to start with LLM pre-training, we need to first understand what is training itself and how it's usually done with large language models. And in general, when we say that we want to train a model, what we mean is that we have some sort of parameterized function. Here, for example, we can see that it's a function L that is parameterized via some set of parameters phi. And what we want to do is we want to find such parameters phi that minimize some sort of target function, this function L, on some set of data. It's represented by X and Y here. And to do this, we usually use methods that take into account gradient information of this function, meaning that if we can find the gradient of this function with respect to parameters phi, what we can do is do updates on parameters phi step by step, performing so-called gradient descent, moving in the direction in which this function has the steepest decline, and such arrive into a point into a minima of this function. And to do this, this function naturally has to be differentiable with respect to those parameters. And when we think about differential functions, we usually imply that those functions are functions of real numbers. And as such, parameters of machine learning models by default are perceived as real numbers. But the thing is, in computer, there is no such thing as a real numbers, because this is a set of infinite cardinality, basically. So you cannot encode the selection from a set of infinite size. And what you can do at best is use some approximations for real numbers. And in computers, those approximations are usually floating point numbers, where we have some sort of grid, a finite grid, where we basically can enumerate every point in this grid and encode somehow a selection from this grid with some finite number, thus representing a number on the real axis with some finite bit width. And the thing about floating point numbers in the way they are usually used is that they're a good approximation in the sense that they provide very huge range, meaning they can represent both very large numbers and very small numbers. And they provide consistent relative accuracy on the entirety of this range, meaning that with usual operations such as addition and multiplication, you get some sort of predictable error with this approximation of floating point over real numbers. But the thing is that those numbers are quite heavy in the sense that you need a lot of information to code floating point numbers. The representation the people use is somewhat complicated, that you need to store the sign and the so-called exponent in mantissa separately to represent floating point numbers. And in general, floating point numbers usually take from 16 up to 64, but usually it's either 16 or 32 bit for every single real number approximation of a floating point number. And might be a lot, and also because the representation is somewhat convoluted with this sign, exponent, and mantissa, it might be hard to perform operations on them, because also processors were designed with support for those operations in mind. They still might not be very energy efficient. And for example, as one thing, and just in general, it might be hard to support more complicated operations with them without modifying the hardware level. And in general, if we talk about energy efficiency and in general efficiency of computations, maybe there are certain data types that are more efficient than floating point numbers. And if we actually look at the modern accelerators for computations, for example, at NVIDIA B100 GPU, it actually has a variety of data types that are not high precision floating point numbers, but these are low precision floating point numbers like FP4, which has only 4 bits per parameter, or FP8, FP6, or integer numbers, which basically represent integer numbers that is a uniform grid on top of real numbers, and for which it's easier to implement operations such as addition, because when adding two integer numbers together, it's quite obvious that you get an integer number back, and the bitwise operations needed to perform the operations on them are simpler than on real numbers. And that's why actually those data types, like either low precision floating point numbers or integer numbers, you can make kernels that perform operations on top of them much more efficiently than in high precision floating point numbers. For example, here we can see speedups of NVIDIA A100 GPU operations on top of different data types when compared to same operations on floating point 16 numbers. So here specifically we have matrix multiplication speedup, and we can see that for low precision numbers, it's basically proportional to how much memory you save compared to floating point 16. So going from floating point 16 to integer 4, you reduce the size of your numbers in memory by 4, but you also speed up all of the computations with those numbers by a factor of 4, meaning that you can actually run your models. If your models were somehow represented in those low precision formats, you get practically proportional speedups to how much you actually compress them in terms of those specific data types compared to FP16. And that's why it might be very beneficial to train models that can be stored in those representations, because not only you get models that are smaller because of low precision, but because you can actually utilize kernels that are simply faster than floating point matrix operation kernels to get practically proportional speedups when running those models. So this is an additional incentive why low precision models are important and why it might be beneficial to train models in low precision. And but there is a problem with training low precision, namely that when you use floating point, it's a very dense grid representation of real numbers, meaning that any small perturbation to those numbers will still land on some points of this grid, and as such, you can actually perform gradient descent on top of them, as I mentioned, because applying a gradient step on top of your model will actually change its representation precisely as it would do with real numbers, or at least close enough. But for example, if we look at the integer 4 numbers here, we see that on this plot, sort of, you can see a representation of if you had the floating point numbers, and let's say you had some gradient steps that you wanted to apply during gradient descent of those numbers. To floating point numbers, you can just add this step, and this point here would just move by a little. But for integer numbers, if you wanted to take the same step, you'd actually see no change in your representation because the step is smaller than your grid size and then your grid step. And as you decrease your bit width, your grid step get relatively larger, and in general, your representations become sort of insensitive to small perturbations, and as such, you can no longer just apply gradient steps to those parameters. So you kind of lose differentiability of your parameters with respect to your loss function, and you can no longer just perform gradient descent on top of those parameters. And there are a few ways to fix this. And let us start by how people usually do this. And the idea is that you actually do not store your model in those low precision representations inherently, but rather have a high precision copy of your model to which you know how to apply gradients. And when you actually perform operations on this model, you quantize it. For example, every single forward pass of your model to obtain quantized representations, perform operations on top of those, But then when you come after you've computed the gradients, you apply those gradients to this high precision copy, which can be done in a straightforward way because those representations are inherently differentiable. And as such, you solve the problem of non-differentiability of your parameters because although you perform all of the computations with your low precision kind of copy of the model, the gradients are applied to the high precision copy, and as such you don't lose any gradients because they really do get applied every single time you perform forward backward pass. However, there is a problem with this approach. So this approach of keeping a full precision copy of the model is standard, but the problem is that this operation highlighted here is the quantization of your model parameters that you have to do every single forward pass to actually obtain parameters that you perform operations with from your high precision copy. This operation is non-differentiable by itself, in a sense that if you want to perform gradient descent, we need to be able to propagate the gradient of our loss through the entire model. But this operation itself is non-differentiable, meaning we cannot propagate loss through it. And as such, we actually cannot apply gradients to apply to those high precision parameters, to the high precision copy that we have inherently. So what we actually have to do instead is, sorry, I think I messed up the order a little because yes, we'll get to the problem of non-differentiability later, but right now let's talk about the separation of quantization itself that we have to do every single forward pass. And basically what we are doing here is we have our weight matrices for a model, and what we have to do every single forward pass is we have to find quantized representations of those matrices. And naturally, we have this sort of discrepancy that we have kind of real parameters, high precision parameters, but we don't use them in operations because we use quantized parameters in operations. And as such, there is discrepancy between what we store and apply updates to and what we use in operations. And naturally, if this discrepancy becomes too large, the training process doesn't make sense anymore because what we update becomes sort of decoupled from what we actually use when using our model. And as such, it makes sense to sort of try and minimize this discrepancy. And that would be just minimize some sort of difference between the quantized parameters x hat that we obtain every single forward pass for the computations and the high precision copy of the parameters x that we actually gets updated after we do the backward pass when we do the step of our optimizer. And to minimize this error, what we propose we do is we optimize the quantization procedure itself. So here we can see that we're doing, usually quantization is some sort of round into a grid, as I mentioned. And before, people often did this rounding in a simple manner that the grid was fitted onto weights in a min-max fashion, meaning that it was fitted for its sort of left end to be exactly the minimum value of your weights and right end to be the maximum value of your weights. This way, the grid would cover the entire range of values that you're trying to quantize. But we argue that this is actually not the optimal way because it's very sensitive to outliers in your weights. And what we're proposing here we do instead is that we fit the grid to the distribution in an MSC optimal way. So minimizing this discrepancy between x and x hat in the form of mean square error between those two variables. And to do this, we make an additional assumption based on observations that for large language models, for already pre-trained ones, people sort of know that weights are almost normally distributed. And as such, if we wanted to optimize a grid for a distribution of an already trained model, we would optimize it for something that very closely resembles a normal distribution. And we extend this idea by saying that we will actually fit the grid to our weights distribution in a way that is MSC optimal, minimizes mean quadratic error of rounding our weights to this grid, so mean quadratic error between x and x hat that would be optimal for a Gaussian distribution. And it's formalized here in the sense that we have this rounding operator with some sort of scaling that determines how exactly we fit the weights onto the grid. And this scaling factor is chosen as to minimize the expectation of quadratic error of rounding a normal distribution to a grid, meaning that if our weights were indeed normally distributed, this rounding procedure would produce an MSE optimal rounding of the weights to the grid that we're using. So any questions about this idea of how we optimize the forward pass by better matching the weights distribution to a grid? So I guess we'll return to this later, and if any questions come up, I'll be happy to answer them. But for now, yes, let's just remember that for the forward pass, we do smart mapping between the weights and the grid that we're quantizing to using the idea of normality of the distribution of the weights. So we do it in an MSE optimal fashion, assuming normally distributed weights. So this is how we optimize the forward pass. And for the backward, as I already mentioned before, there is a problem that this rounding operator that is inherent to a projection is not differentiable. And people have known about this problem for a while. And the standard thing, the standard way to address this problem is to use the straight-through estimation. And what it is that if we try to draw the plot of this rounding function, it would be a step function in a sense that it would have zero gradient anywhere except the places where you actually jump from the one quantization point to the next one, and there you'd have an infinite gradient and a jump in your function and a sort of a step. And what the straight-through estimation does is says that if your steps are small enough, then this function is in general very close to simply a linear function with a linear coefficient of 1. And what we can do is say that the gradient of this step function, we can approximate it with the gradient of a linear function with a coefficient of 1, which is just 1 everywhere. So basically, we can approximate the gradient with respect to the unbounded values as the gradient with respect to the quantized values when doing the backward pass. So on the forward, we have x, and we obtain x hat by rounding. This operation is not differentiable, but the approximation says that we can say that the gradient with respect to x can be obtained by just reusing the gradient with respect to x hat that we have already somehow obtained through backpropagation. So we sort of can approximate backpropagation through this rounding operation by just saying that the gradient is 1, is propagated as is through it. But there is a problem with this approach, is that if we use this smart distribution fitting for our grid on the forward pass, and we look at the normal distribution and how a grid is fitted to it, we'll see that there are some portions of the distributions that fall outside of the grid, which naturally happens because those are sort of outliers in our distribution, some tails that happen very rarely, and as such affect our mean square error by a very small margin, and it's better to just leave them outside than try to accommodate. So the trade-off results in the fact that tails of our distribution fall outside of the grid, and naturally we have a very large quantization error for those tails. And in practice, if we wanted to do straight-through estimations through points that happen to be in those tails, it would not make much sense, because when quantizing, those values simply get rounded to the nearest grid point that might be very far away from them. And when we apply gradients to the underlying high precision representations, they will switch left, they will sort of move left and right, but it wouldn't change anything with respect to how we actually do computations, because in the next forward pass they will still get rounded in exactly the same way to exactly the same grid point. So in general, the gradients for points that fall outside of our grid are unreliable because of how far away the updated weight is from the quantized weight that is actually used in operations. And extending this idea, what we might want to say, and what we did in the paper, is that when doing the backward pass, the thing that we want to minimize is we have this high precision copy of the weights and the weights that we actually use in operations. And on the forward pass, we minimize discrepancy between those two by minimizing the quadratic error between them, as we did with distribution fitting. But on the backward path, we also want to ensure that the gradients that we apply to them actually make sense. And we can formulate in this form of quadratic error between the gradients taken in this point between the gradient in the point where it's applied and the gradient in the point where it was sort of calculated, because we actually used this value for this parameter on the forward pass. So this is sort of, again, the discrepancy between the full precision weights that we update and the low precision weights that we use in computations, but now in the form of gradients that we apply to them and then we calculate. And while we don't have explicit values for this gradient, because we never actually do unquantized forward passes, we still can use this idea that if maybe this quantity might be very large if the difference between W and W hat is large. And this again reiterates this idea. So if the point changes too much during the quantization on the forward pass, like it gets rounded way too hard, then probably the gradient that we estimated for it will not be a good approximation for the real gradient that this point lying way over here has. And what we can do with this untrustworthy gradient is we say that instead of applying this gradient that had huge distortion because of this rounding on the forward pass, the better thing to do is simply not to apply it, to completely zero it out. And we formalize it in this idea of masking on top of our gradient estimation. So what we had initially for straight through estimation is we just had this differentiable, this gradient with respect to x equal to the gradient with respect to x hat. But what we're saying is that we can extend it with a binary mask that is chosen on how much x changed due to quantization on the forward pass. So this is somehow a measure of discrepancy between the weights that we update and the weights that we actually use in computations. And what we say is that we can build this binary mask by using some sort of threshold on this error that would result in this sort of pattern where weights that are closer to quantization grid points are sort of deemed trustworthy because they didn't change too much during the forward pass, but values further away from grid points, like the red area here, actually we say that it changed too much during the forward pass, and the discrepancy between those two values is too large, and it's better to simply not apply any gradients to them instead of applying this untrustworthy gradient. So what we do here is we apply this binary mask during back propagation through this sort of rounding to a grid operation. And to choose this threshold, we actually say that it makes little sense to leave gaps in our quantization grid, because we observed it both in practice and logically. It would make little sense for a point here not to get gradient, because if it does get gradient, it actually moves left or right and can change its value. So it makes more sense to apply gradients to every single point inside the grid. So we chose this sort of factor for trust of values for this threshold for our binary mask to be half the grid interval, such that it covers all of the inner points of the grid, but also sticks out outside a little. So it's this idea about zeroing out the gradients to points that fall way outside of the grid clear to you? Are there any questions?
I think there are two questions by Pavel in the chat. I could read them out. So the first,
please do. I don't have it open.
yeah, all good. The first question is: can performing in-training pruning or lasso regularization improve the problem with the outliers in this context? And the second part is: does it make sense to penalize weights for numerically overflowing the target quantized range via introduction of an additional loss term?
So I think I'll answer the second question first. So what we did in practice, as I said, we fit a grid to a distribution in this MSE optimal way. But what we actually also have here is that we normalize the weights by its L2 norm practically, meaning that even if this assumption about the normality of the weight was right, no matter how you scale your grid, some weights will still fall outside. And actually, this amount of weights that fall outside can be computed even in theory by just computing the mass of those tails that fall outside for the MSE optimal fit. So it doesn't make sense to penalize them additionally. And regarding general penalizing the scale, we use L2 norm or scaling for the weights, meaning that the actual scaling for them can be way different, but we sort of normalize it to a 0-1 normal distribution. So even if X was a normal distribution with very large variance, normalizing by its L2 norm would produce a 0-1 normal distribution for which we have those optimal coefficients and for which it is sort of expected that some values will fall outside of the grid, because this is a trade-off of grid being denser in the middle where there are more values to be expected, and some values falling outside, which is sort of inevitable when you're dealing with distributions that have sort of infinite tails. And the first question, could you please remind me what it was again?
Yeah, I think the first question was: can performing in-training pruning or lasso regularization improve the problem with the outliers in this in the context that you were mentioning?
Okay, so in general, we didn't look into pruning on any level beyond a very small level, because later I'll show that we actually have combination of our method with sparsity, which can be thought of as some very local pruning, but on a level higher than just some adjacent values in structured sparsity, we didn't look into pruning. Okay, thank you. So to reiterate, this is the basic formulation of the QuEST algorithm. So what we do on the forward is we quantize our weights in a way that it would produce MSE optimal quantization if they were distributed normally. And on the backward, we backpropagate through the separation that is not inherently differentiable by using straight-through estimation with an additional binary mask that was chosen via analyzing quantization errors of weights on the forward pass. So this mask is not built using the gradients themselves, but rather what happened on the forward pass. And up until now, I mostly mentioned that we quantize the weights, but that's not all the truth, because actually we quantize both weights and activations. And it's important because the speedups I mentioned, those are speedups for fully quantized matrix multiplication operations, meaning that both tensors that you're multiplying together are quantized, meaning that both your weights and activations have to be quantized. And this sort of quantization that has to happen during forward pass of the training, we can use exactly the same quantization scheme to quantize activations too, and thus perform matrix multiplication between those in the low precision format, which would mean that the resulting model that we obtain would be optimized for both for quantizing both weights and activations, and as such, for using those specific low precision matrix multiplication kernel later when we will want to deploy it. But we'll talk about this later. And now let's talk about this additional things. So this is basically the idea behind QuEST, but we actually do one additional thing on top of this that makes our training produce even better results and become in a way a little more stable. Is that, as I said, we kind of know that large language models weight distribution often are close to normal distribution, but actually there is a way to ensure that it almost perfectly matches the normal distribution, and that is applying the Hadamard transform to whatever you're quantizing. By doing that, by applying the Hadamard transform to the matrices that you're quantizing, is the results in distribution of values in those transformed matrices is guaranteed to be normal. And when rounding it to the optimized grids, we can actually say with certainty that this rounding would be performed in an MSE optimal way when using this idea together with QuEST that optimizes the MSE feed for quantization under this assumption of normality. So what I'm trying to say here is that instead of just assuming normality, we can actually sort of enforce it with by inserting the Hadamard transform inside the quantization scheme. And more specifically, the way we would do it is our model is mostly comprised of linear layers, and here we have two algorithms for a forward pass of QuEST and for a backward pass of QuEST, of the full QuEST algorithm that actually uses the Hadamard transform. And on the forward pass, we have full precision weights and activations. And first thing we do is we apply the Hadamard transform to both of them. Then we quantize both of them. Here, the quantization is this projection operator to some sort of grid with an optimal scale. And then we perform matrix multiplication in this low precision format. And what we have to store from this matrix multiplication is actually those two low precision weights and activations, and those aforementioned masks here for masks that depend on the difference between the quantized and the unquantized tensors. I don't have the notation, but those masks M alpha star are actually just those binary masks that will use the backward pass during the backward pass. And on the backward pass, we reuse those quantized weights and activations, those masks, and the newly arrived gradient from the following layers to perform gradient computations for the weight and for the inputs too. And the thing we should note here is that those gradients are not quantized. And even if we have to perform matrix multiplication between those unquantized gradients and quantized weights, we'll have to do it with higher precision matrix multiplication kernels, because this is still a full precision operation because the gradients are not quantized. And as such, we don't get speed up during the backward pass. And in general, this means that we don't get speed ups during the training at all. And it means that this algorithm doesn't allow us to train faster. What it does, it allows us to produce models that use both quantized weights and activations and use more efficient kernel for forward passes and for inference, but the training itself is not sped up. And one additional thing why this Hadamard transform that we inserted, so the first idea why it's useful is because it improves the fit between the values that are quantizing and the grid that is chosen to be optimal for a normal distribution, because Hadamard transforms normalizes your distribution and makes it normal. But another thing is that on the backward pass, we naturally have to back propagate through this Hadamard transform, and this means we have to apply the inverse Hadamard transform to whatever gradients we're computing. And this shows additional interesting point, because if you remember, the masks that we applied during the backward pass that were based on the quantization error are binary, meaning that some portion in this setup, some portion of the weights doesn't get any gradients. It gets fully zeroed out. And the problem with it is that if we look at this, the weights that don't get gradients fall outside of the distribution, meaning that if they don't get updated, they will still lie outside of the distribution, meaning that they will never get gradient and they will practically always remain stale during training and unused. One thing to counter it naturally is using weight decay such that those values, even if they don't get any gradient, they would slowly drift towards the center, meaning slowly drift towards the quantization grid. But a better way is to actually use this Hadamard transform, because as you can see, when we apply this binary mask to the gradient, we actually then, to obtain the actual gradients with respect to our full precision weight copy, we have to perform the inverse Hadamard transform over this masked gradient. And doing this makes it such there are no fully zero entries. So some entries of this tensor are zero, but when you perform this inverse Hadamard transform, it reshuffles all of the entries, basically performs some sort of rotation on top of this vector, and now all of the weights of the original weight copy that we have here get the gradient, and we get rid of this problem of stale weights, and we actually have an ablation showing that this Hadamard transform reduces the number of stale weights during training, and this is another reason why Hadamard transform is useful. So firstly, it improves the distribution fit, and secondly, it reduces the number of stale weights during training. So now that we've discussed the scheme, let's discuss the results that we obtained and later interpret how we can interpret them. But firstly, let us look at this plot. So this plot shows the C4 validation loss of models of llama family from 30 million parameters to 800 million parameters trained on the C4 training set for the amount of tokens that is 100 times the number of parameters. For example, this 30 million parameter model here was trained on 3 billion tokens, and this 800 million parameter model was trained on 80 billion tokens. And we trained those models of different sizes, namely 30, 50, 100, 200, 400, and 800 million parameters on the corresponding numbers of tokens. And we did it for with and without QuEST quantization. For QuEST, we used quantization to 1 bit, 2 bit, 3 bit, and 4 bit for both weights and activations. And what we can see here is, first, an interesting thing is that 1 bit training, meaning that all of the forward pass operations, all of the matrix multiplications were performed on binary weights and binary activations. This still converges and provides a stable training and stable training law. And on its own, it's already interesting how this setup, where for every practically tensor in your network, you have only 1 bit of information, it can still stably converge and provide results that are noticeably better than other quantization precisions, but are still, in a sense, somewhat competitive. But what is more interesting, what we can see here, is that the optimality in terms of model size to model error trade-off seems to be around 4-bit quantization, meaning that if we train with QuEST for both weights and activations quantized to 4-bit, we get Pareto optimal models on this size to accuracy trade-off, size to validation loss trade-off. But there is a caveat to interpreting those results, because, as I said, the number of data we used is proportional to the number of parameters, and at the fixed model size in megabytes, models that were quantized harder have more parameters, and as such, they have seen more data, and a more careful analysis of what's happening here is needed to actually make any claims about optimality. And this is what we do next in this section of the paper, where we interpret the quantization scaling laws to find the real optimal precision. So maybe any questions up to this point about the method itself?
You can unmute, Paul.
First of all, thank you for answering prior two questions. And quick question, did you try to experiment with adding random noise to the masks and or drop out? Like, how does that influence the training convergence plots?
Actually, no, we didn't try to add random noise. We tried it. We tried a few things where we would try to do something with those clipped values, like we try to accumulate them or apply with smaller learning rates, but none of those experiments showed any improvements. And we decided that simple binary clipping is the best thing we can do here. We didn't try to insert an additional noise. But this might be an interesting direction for future work. For example, one other thing we might try to do is make it a smooth function instead of a binary mask, but inserting noise is also an interesting proposition. We might consider it for future work. Thanks.
Thanks. And while I'm still here, is like concept of the lottery ticket applicable here, do you think? Like when you have an ideal structure which could be applicable to larger scale models, for instance. So let's say you trained a smaller scale model, and you kind of have a topology of your mask or your weights, and then you can just extrapolate that onto the bigger model without retraining.
Okay, I'm not sure if that happens because, as I mentioned, one of the things the Hadamard transform does is that it shuffles the mask. And the way we verified it in the paper is we had this study where we looked at masks during training of a single model at different steps, and we saw how consistent it is. And we saw that when we actually use the Hadamard transforms, the masks kind of shuffles a lot during training, meaning that weights adapt a lot. And as such, I don't think that the masks that we learn on its own is that interesting because it might shift during the training of one model itself, and it's probably not transferable to other models.
Thank you.
Okay, so if there aren't any other questions, I'll go towards the scaling laws discussion part of this paper. And in general, when we talk about scaling laws, what we mean is that we want to try and predict or describe the final loss of our model as a function of its parameters. And for large language models specifically, the parameters of the models are usually dictated by the literal number of parameters of this model and the amount of data it was trained on. There are other things that are very important for the optimization procedure, like the exact architecture of your model, like the trade-off between its depth and width, and the learning rate, the optimizer. But assuming all of those things are either fixed or chosen optimally, you have two variables that you can easily change in your training processes, like the general size of your model, dictated by the number of parameters in it, and the amount of data it was trained on, usually described in the amount of tokens it has seen during training. And the way people have been describing this for quite a while now is in form of this scaling law, initially proposed by Hoffman and co-authors in their paper on optimality of pre-training from a compute standpoint, where we will see three distinct terms of loss of a model. One is error that is irrecoverable on your training set, that the loss function has some innate error inside of it. Another term that describes how your loss scales with respect to your number of parameters, and a third term that describes how it scales with the amount of data that your model has seen. And the interesting part about this scaling law on its own is that it sort of decouples data from the number of parameters, and the numerous papers reproduced this idea that those two terms are indeed sort of decoupled, and you can treat them separately and make some and infer some ideas about optimality from this scaling law. And as you can see, this scaling law on its own originally didn't include any idea about quantization or training precision. And what we do, which is not a novel idea of its own, because it was used by a few other papers trying to describe scaling laws of precision, is we introduce some sort of efficiency factor, like an effective parameter count multiplier that depends on the precision that you're training in and also the quantization method itself, but let's just denote it by precision, that multiplies your parameter count and doesn't affect the data and the inner parts of your scaling law. So basically what we're saying is that quantization during pre-training only has effects on the parameter count of your model in the form of an effective multiplier. And by setting this effective multiplier of precision, of full precision to be 1, we recover the original scaling law and sort of normalize this effective scale for all other precisions. And to actually somehow use this scaling law to make predictions, what we need to first to do is to fit this scaling law in the sense that we need to fit parameters A, B, E, alpha, beta, and also effective multiplier for every single precision that we want to analyze by training a number of models and fitting this the difference between the predicted performance and the actual performance with some error function. And here we follow the setup of Hoffman and co-authors, where they used, I think, ridge regression on top of logarithm of those loss values to fit all of those parameters. And what we obtain is that this effective parameter count, we fixed it to 1 for 16-bit. And we say that 8-bit produced somehow effective parameter count that is larger, but we theorize that this is just noise because it probably cannot be larger. And what it means is that 8-bit pre-training with QuEST is practically indistinguishable from 16-bit pre-training in the sense that it has exactly the same effective parameter count and you don't lose any of the performance because you quantize. So the predicted performance and by extension the actual performance of models quantized to 8-bit would be exactly the same. However, for hardware quantization, we see that it starts to drop off rapidly. For example, for 4-bit, this effective parameter count is 0.7. For 3-bit, this multiplier is 0.4, and for 1-bit, like the binary quantization, it's actually just 2%, meaning that from this point of view of scaling loss, a model that has 1 billion parameters, for example, quantized to 1-bit, actually is practically the same as the model that only has 20 million parameters of full precision. And after fitting those effective parameter counts, we can try and analyze of what it exactly says about quantization. And if it would make sense for this effective parameter count to only get lower as you decrease your bit width, what is actually optimal? And to do this, we first of all analyze the scaling law in a very specific regime. And this regime is based on the idea that in the Chinchilla paper, it was determined that from the training compute standpoint, the ratio between D to N for optimal pre-training was around 20. But nowadays, meaning that for every parameter, you had 20 tokens in your training set. But nowadays, models are usually trained with this ratio of often larger than 1,000, meaning that for every single parameter in your model, you have more than 1,000 tokens in your data set. And this is dictated by the idea of that runtime compute of your model is not free, it's not negligible, and it makes sense to train smaller models for way longer beyond some compute optimal bound to then have a performant model that is actually cheap to run because it's so small. And we can take this idea to extreme by just taking the limit of D to N to infinity to arrive at this scaling law, the overtraining regime, where we will simply practically discard the second term of this scaling law, the data-dependent terms, by saying that we trained our model to saturation, to full saturation with data and obtained the best possible loss possible for this model size. Because again, what interested us is not the optimal training, but how cheap we can run the model afterwards. So this says that this would mean that we can train our model to saturation and have the best performance at a certain runtime cost during inference. And what we can remember is that runtime costs during inference can actually be described. The quantization has a huge effect on runtime costs during inference in the sense that lower precision have proportionally cheaper inference cost, in the sense that the maximal throughput of your model and latency is actually inversely proportional to your precision. Like if 1-bit quantization is 16 times faster than full precision 16-bit numbers. And what we can say is that we can formulate this in the sense that we will describe our runtime costs f to be proportional to precision and to the number of parameters in our model. And this would indeed describe, for example, the throughput of our model. And then what we might want to do, considering that we're interested in inference runtime, is we might want to ask a question such as, what's the optimal N and P such that the runtime cost is below some threshold that we put ourselves regarding the inference cost of our model. And then we can write this minimization problem where we want to minimize the loss of our model with respect to the number of parameters of our model and precision, such that we respect this maximum runtime cost that's proportional to both number of parameters and precision. And when writing this scaling law, we see that, first of all, it has an obvious solution where you just set f to f max and then choose this number to be as large as possible. So this ratio of effective parameter multiplier divided by precision is actually what determines what precision you should choose in this overtraining regime. And if we plot this quantity like effective p divided by p, we see that it peaks around 4-bit quantization. So first it grows almost linearly because effective p is practically 1 for very high precisions, and 1 divided by p increases. But then at some point, effective p starts to drop off rapidly, and even the additional benefit of faster inference doesn't save you from the fact that your loss is pretty bad. And as such, you have some sort of peak, a maximum somewhere, and we show that this peak for QuEST is at 4-bit per parameter, meaning that our method is optimal for overtrained models around 4-bit per parameter. And this is what we mean when we say that our method is optimal for pre-training at 4-bit. It means that it's optimal in terms of this runtime cost of overtrained models during inference. So any questions about how we came to this conclusion? Okay, so if not, I'll continue because we don't even have that much time. So what you can also see in this plot is that we have QuEST for integer grids, but we also have QuEST for FP4. And what I mean by that is that quantization is just rounding to a grid. And we have a way to optimize how we actually round to this grid for practically any arbitrary grid by saying that we optimize it in a sense of quadratic error of rounding the normal distribution to that grid. And as such, we can also optimize rounding normal distribution to a floating point for a grid, and we can train models that would be inferenced in the FP4 format, and we can also fit the effective P for those models. And on this plot, you can also see this effective P. And an interesting thing we observe is that the effective P for FP4 seems to be worse than for integer 4. Meaning that the int4 is actually somewhat better for pre-training than FP4. And we have another idea why that might be happening, because if we'll actually, we had an idea about the quadratic error of rounding during forward pass being important, we explicitly minimize it via the scale optimization for quantization. And if we actually take a look at how this quadratic error relates to the resulting effective multiplier, we can see that there is some sort of dependency between those two values, and the FP4 appears to be simply worse both in terms of this quadratic error, so it simply has higher quantization error of normal values, normally distributed values to this grid, and as a result, it also has worse effective parameter multiplier. But our method is still stable for FP4 and still can produce models that are definitely Pareto optimal to 8-bit and the 16-bit in the same regard as we just discussed for integer grids. And one other thing we can do for our method is we can also combine it with sparsity. More specifically, we're interested in the structured sparsity of that are supported on the latest generation of NVIDIA GPUs, where out of every 4 consecutive values in the matrix, exactly 2 are 0, and this allows us to store those matrices in a very highly compressed format and also run matrix multiplication with them very fast because of the specific kernel support. And what we find that it also produces stable trade-ins, but it's somewhat worse than integer form in terms of this optimality we discussed before. And one last thing that I'll mention about our results is that our method can naturally be used for weight-only quantization. We simply don't have to quantize activations. We won't have as good of a kernel support for the inference, but there are ideas of why it would still make sense to quantize weights, because, for example, when running decoding, like generating one token at a time with LLMs, you're actually more interested in how much your weights are compressed in terms of memory than this kernel support, like the maximum throughput. And that's why it makes sense to analyze weight-only quantization as well. And if we plot this effective P over P for weight-only quantization, we will see that we find that 3-bit is actually optimal for this setup. And yes, it can be analyzed in exactly the same way we analyzed full quantization. And we get that for weight-only quantization, quantizing a little harder makes more sense, which is sort of expectable. And in general, that's about it with the results that we have. And if you have any questions, I'll be happy to answer them.